Well, welcome back. Hello. So in this video, we're going to learn about how to handle something that we don't have a graph of. We just have an equation. We have a position equation in terms of time, but we don't have a graph. And how do we find instantaneous and average velocities from that? Okay, so before we had a graph here, or as an example, and now we're not going to have a graph. So what are we going to do? So let's suppose that instead of giving a graph, we're given a function like this. Let's just say a polynomial function. We're going to be working mainly with polynomials, which is nice and easy for us. We could graph the function and then draw an approximate tangent line and use the graph paper to help us figure out the slope of that tangent line. Or we could just use differential calculus. Oh yeah, it's going to be good. Okay, so the velocity is defined as the limit as change in time goes to 0 for displacement over time. So in calculus, what that means is the derivative, dx, the derivative of position with respect to time. It's actually pretty easy to take a derivative. So let's say our position derivative, or position equation looks like this. It's a polynomial, where a is a constant, some number, and times t to the n, which is another number, just any number. Then we are going to, so the derivative of position with respect to time is you just bring this n down, multiply it by the a, and then subtract 1 from the exponent. A lot of you guys should be very familiar with this. Okay, so let's get some practice. All right. So we're given that the function x, is equal to this right here, 3 minus 6t plus 3t squared. What is the instantaneous velocity at 6 seconds, and what is the initial velocity? Okay, so why don't you take time. Actually, I'll do it with this first one with you. So first we need to find the velocity. So velocity is equal to the derivative of x with respect to time. And I know that you use the primes like f prime to show a derivative in calculus. There's a special notation. If you're taking a derivative with respect to time, it's a dot on top. So velocity is equal to x dot. So since there's no time here, there's no t, so it's t to the 0. If we bring down the 0 right here, anything times 0 is 0, so the derivative of 3 goes away. The derivative of minus 6t, right here, this part right here, so t to the 1, so if it's minus 6 times 1 times t, and then you subtract 1 from the exponent, so t to the 0, plus, and then let's see, t to the, this part right here, so it's t squared, so you have this 3, and then you bring down that 2, and it's t, and you subtract 1 from the exponent. So we put it all together. This is equal to negative 6 plus 6t. So that's our velocity with respect to time. Another way of saying that is your x dot equation. Okay? Now, we want to find the velocity at 6 seconds. So the velocity at 6 seconds is negative 6 plus 6, and then you just put in 6 for time. 6 times 6 is 36, minus 6 is 30, and we just put in some units there because I need to do that. What is the initial velocity? So that we assume is that time equals 0. So it's negative 6 plus 6 times 0, so it's negative 6 meters per second. Now, let's see. Here is, well, we'll take that later. Okay, so let's try another example. Oops. A particle travels from A to B following the function, same function. What is the average velocity? Ooh, average velocity. Okay, so we could take the initial velocity, which we got at -6, right? From before, and the final velocity, which we got at 30, and average them together. So 6 plus 30 divided by 2. So that's 36 divided by 2 is 18. Let's see if that works. All right. All right, so let's remember that velocity is change in position over change in time. Displacement over change in time. So we need the position at the final position. So the position at 6 seconds minus the position at 0 seconds divided by our change in time. So a position at 6 seconds, I'll try and do this without a calculator. Let's see, 3 minus 6 times 6 minus 3 times 6 squared, 36. I want a calculator. Ooh, got a calculator. Okay. 3 minus 6. So this is equal to 75. And position at 0 is 3 minus 0 minus 0. Whew, equals 3. So our change in x is 75 minus 3. That's 72. And our time is 6 seconds. So our velocity is equal to 72 divided by 6 equals 12. All right. That is not 18, which is really, really, really important to see. This only works if the acceleration is constant, but it's not always going to be constant for us. This velocity equals displacement over change of time is always, always, always true, without exception. You use this. Do not take the average of the velocities, because the acceleration could not be constant. In this case, second derivative, it might be. I'm not quite sure. This doesn't work out. This does. Always use displacement over time. All right. So I want you to try to find the velocity of this function and the instantaneous velocity at 2 seconds. All right, go. Welcome back. Okay, so let's see. The velocity of this function. Let's write this function another way. So x is equal to 1.5 minus 4.2 times t to negative 2 plus 5t. So then the derivative of x with respect to time, dx dt, is equal to x dot, which is equal to the velocity, is equal to, bring down the negative 2, so 8.4, so negative 8.4 times t, and you subtract 1 from that, so it becomes negative 3 plus 5. Okay, so this is the velocity. The velocity function is negative 8.4 times 3 to negative 3 plus 5. Find the instantaneous velocity at 2 seconds. So the velocity at 2 seconds, I'm going to do this. So negative 8.4 divided by 2 cubed plus 5. Okay, so 8.4 divided by 8 plus 5. 6.05. All right, cool. It's kind of fun, huh? Acceleration. Any change in velocity over a period of time is called acceleration. The plus or minus indicates the direction of the acceleration. So acceleration means both speeding up, slowing down, and turning. And we'll get to the turning part much later in the semester. Uniform or constant acceleration equation, then you would use your kinematic equations that we know and love from before. We'll get to those later. Okay, so we will stop here and we'll do the graphs of motion next video. Take care. Bye-bye.